Guzmal here. Today we're going to talk about why you can't add zero point 0.1 plus zero point 0.1 plus zero point 0.1 and get zero point 0.3 in Python or most programming languages. Now, we all know computers store information as bits, and we typically recognize that the bit 0 represents the number 0, and the bit 1 represents the number 1, and the bit 10, we are very clever when we are doing our binary counting. We know that 10 is obviously 2. We have the t-shirts that say there's 10 kinds of people, those who know about binary and those who don't. Hilarious, we're ingenious. And then we go to 11, and that's obviously 30, or maybe it's -2, or maybe 10 is actually -0, and we kind of are confused because we can do simple things like just basic positive integers or non-negative integers, but how do we even represent a negative integer using bits? Um, and so our basic idea of just using sequences of powers of 2, like 0 is 0, 1 is 2 to the 0th, 10 is 2 to the first, 11 is 2 to the first plus 2 to the 0, it doesn't work out, because I mean we could have 1 0 0 0 equals 1 and 0 1 0 0 equal 2. Why not? We could do that. We could have 1 represent a snake and 10 represent a cat sitting next to my arm trying to eat my hand. We could do anything we want. It's called a mapping a sequence of bits to a given particular choice of values is something we could do. um, and there's lots of things, though, that we want to represent. We don't need to always represent the snake or the cat, although actually sometimes we do, and we'll see that in hash tables and stuff. But things we want to immediately represent are things like pi. Wait a minute. Pi does, no matter how many digits or bits we have at our disposal, we can't represent pi perfectly. So even if we have an unlimited sequence of bits, we have trouble. But on a computer, we have a limited number of bits to represent any given value or number. Similarly, heck, it doesn't even have to be pi. 1/3 is 0.33333333. And in binary, wait a minute, how do we even represent fractions in binary at all? Well, we can do 1/2. 1/2, we can think of that as 0.1 in binary. And obviously, that's definitely 1/2. And 0.11 would be 1/2 plus 1/4, because the second one would represent 1/4 and first one would represent 1/2. We add them together, and 0.111 will be 1/2 plus 1/4 plus 1/8. Okay, so we can do fractions in binary using bits, and this is okay. We won't worry about negative numbers. We won't worry about anything positive. Binary representations of numbers, and with 3 bits, we can represent 0 or 1/8 or 1/4, which is 2/8, or 3/8, or 1/2, which is 4/8, or 5/8, or 3/4, which is 6/8, or 7/8. So 1, 2, 3, 4, 5, 6, 7, 8ths, or 0/8. We can represent with 3 bits. Of course, that means that we cannot get exactly to any other number. So if we want to get 1/3, then the closest we can come is 0.011. If we have 3 bits, we can keep adding bits, and you notice we get a repeating fraction, a repeating sequence of numbers. Repeating sequence of numbers in binary, just like we do in decimal. So rather than 0.333333, we get 0.01010101. Okay, well that's fine. That's great. That's actually okay. We're feeling pretty comfortable. But there's complications, and and there's other numbers that cannot be represented, like 1/10. 1/10, which we would think could be represented with 0.1. No, wait, 0.1 is 1/2, because that's what we do when we're counting in binary. So in binary decimal, 1/10 is not 0.1, but 0.00011, which is not even exactly 1/10. It's 3/32. It's as close as we can get. You might argue that 4/32 is closer. No, that's 3/32 is closer. But we can get unexpected results if we add 1/10 plus 1/10 1/10, though, because that gets translated into 3/32 plus 3/32 plus 3/32, which is 9/32. But that's not as close to 3/10 as 10/32 is, which we could represent using, in this case, 5 bits. So even when we stay within our bounds, we break our own rules, so to speak. And so 0.1 plus 0.1 plus 0.1 is not 0.3.